So, welcome. So this time we're going to continue with our studies, and we finished AC theory last time, and now we're going to look at basically an extension of this, which is electromagnetic waves. Frankly, this gets into it's one of those chapters where I want some of it, but I don't want all of it. I want you to know about the bit that we don't particularly discuss, but I'll try and be clear about what I want out of this. And we start off talking about good old, our old friend Maxwell. And, you know, basically we have Gauss's law, the total electric flux through any closed surface equals the net charge inside that surface decided by epsilon naught. And then we have the magnetic equivalent of Gauss's law, which is the net magnetic flux through a closed surface is zero, just because they're continuous loops. And then we have basically, which one is this? E dot ds is equal to minus d5 by dt. Is this, whose law is this? Yeah, Ampere's law. And basically EMF over, which is over a line integral of electric field around a closed path equals the rate of change of magnetic flux through any surface area bound by that path. And then we have the magnetic equivalent, which we've not seen before. Maybe we saw it no, I don't think we've seen this before. B dot ds is equal to mu naught I. Well, we saw that before. Whose law was that? Yeah, sorry, what was this one? Whose was that? Minus d5 by dt is equal to... It's a bit like Faraday's law, isn't it? Yeah. And then we have Ampere's law, and then it's modified, though. We've got this extra term in here, which is bringing in, if you think about it, this is linking... well, it's more advanced than we've seen before. The line integral of magnetic field around any closed path is the sum of mu naught times the net current through the path plus epsilon naught mu naught times the rate of change of electric flux through any surface bound by the path. And normally we see mu naught's always about magnetism, and we see epsilon naught's always about electrostatics, and now we're seeing them both in the same equation. All I want you to know is that those equations exist and that they are called Maxwell's equations, and that you've done some of them. So back in the day, people were messing with electricity and batteries, and they found that they could, and coils and inductors. What they found was that they could have this weird situation where if they caused a spark to occur by having an induction coil which causes a high voltage, which causes a breakdown, ironically they could induce a spark in a coil that was reasonably close by but not connected. So we basically got electrical energy going to some kind of invisible kind of energy, which was then picked up again by the second coil. Electromagnetic, basically. So we say Hertz used a LC circuit as a transmitter and another LC circuit as a receiver. He was able to show that energy moved from transmitter to receiver via EM waves. Now that's kind of amazing, because that means that you can then transmit energy basically through the air using electromagnetism. And if your intent is to transmit information, you don't need that much energy, just a little bit of energy just to cause a deflection on a needle somewhere will send them the message. So if we look at the third and fourth of Maxwell's equations, then we see that we can solve them, and this is way beyond what we do, but basically we have two partial differential equations. We have a partial differential equation, d2e by dx squared is equal to mu naught e d2e by dt squared, and we have this constant in between. And, oh, I'm sorry, we can also get d2b by dx squared is equal to mu naught epsilon naught d2b by dt squared. And we solve these things and we get a general wave equation, which is d2y by dx squared equals 1 over v squared d2y by dx squared. And so we look and we say, well, if that's 1 over v squared, and that corresponds to that, then my v is equal to the square root of that, which is c equals 1 over the square root of mu naught epsilon naught. Well, that's a constant and that's a constant. And if I put the numbers in, I get 9 times 10 to the, what's the speed of light?
-7.
How fast does light go?
300.
What is it? Oh yeah, 3 times 10 to the 8, sorry. 8 meters per second. And that's what it works out to be. So we can derive the speed of light, and that's kind of amazing, really. And so we start playing with it. And so I don't particularly want you to remember that. I mean, I suppose I wouldn't ask you it, because I don't expect you to know mu naught, and I don't expect you to know epsilon naught. I suppose I could ask you, what is the speed of light in terms of, that would be a fair question. What is the speed of light in terms of the permeability of free space and the permittivity of free space? And that would be a useful thing to know. So that yes, okay. The next thing I want you to know is that speed of light is equal to E over B, which equals E max over B max. So C is equal to E max over B max. And there's always this question about how do you remember stuff like that? B max times C is equal to E max. And the way I remember it is it goes A, B, C, D, E. It's going alphabetically at that point. I must confess, I visit this area about once every semester for about a day. And, you know, this is not the kind of equation, if you wake me up, I will tell you. It's like, I gotta refresh myself on this. So we say, consider an electromagnetic wave. If the maximum component of magnetic field, let's just draw it. So here's my electric field, and then here's my magnetic field, and it's kind of like, they're at 90 degrees to each other, because that's the way it goes. And this would be E, and this would be B, and they're going in this direction. And the E induces the B, and the B induces the E. So this is, again, this is not trivial stuff. In every other wave system, we need a medium. We need something that the wave rides on. So sound needs air. It's just the way it is. In this case, light doesn't need a medium. They thought for a long time there was a medium. They looked for the ether. And it was when they couldn't find it that there was a huge revolution in physics. That's when Einstein came in. Because he started saying, okay, there's no ether, so how does this work? Whereas everybody else was saying, there must be an ether. There must be a medium to carry the waves on. Because it's just so logical, because they've seen it so many times. And now suddenly, along comes Einstein who says, okay, you can't find it, it's probably not there, let's just go on. Let's see if we can get these effects using other methods that don't need an ether. A tremendous revolution. So it's a weird kind of situation where one wave propagates the other and they're interlocked. We look at light, which comes from way, way, way across, well, beyond the galaxy. We can see light with a telescope. We could see Andromeda if it was brighter. Andromeda occupies the same angle in the night sky that the moon does. It's about the same size, but it's so faint we don't notice it, unless we have a telescope. But we do get light from there. We can look at that light, And we're looking at light, which is, many light years old. And we can see with telescopes, we can see galaxies that are 1 million light years away. Those photons, from our perspective, have been traveling for 1 million light years. Taken 1 million years to get to us. They have not lost any of their energy. They are. You couldn't put, what else has lasted for 1 million years unchanged, and yet light does it, all the time. It's very strange stuff. Anyway, so we say, what do we know about this? We know that the magnetic field max, Bmax, is equal to 2 times 10 to the minus 3 Tesla. And Emax is what I want. And what's the relationship? And so we go alphabetically. Bmax times C is equal to Emax. And so 2 times 10 to the minus 3 times 3 times 10 to the 8 is equal to Emax. So 6 times 10 to the 5, by the look of things, is equal to Emax. So Emax is equal to 6 times 10 to the minus 10 to the 5. And what is it going to be? It is going to be what units for Emax? Volts? No, that would be a Vmax. So what does E come in? Remember, it's just an electric field. So there's 2 possibilities. One is newtons per coulomb. And what would also work? You're halfway there. Volts per meter. Yeah, so either one would do. So it's just an equation. I must confess, it's like we don't do much with it beyond this. It's a bit like, one of physics's cul-de-sacs as far as I'm concerned. It doesn't really take me anywhere. But later on, if you did EE, you'd continue with it, etc. So electrical engineering, or if you did physics, it would continue. Okay. So let's imagine drawing these things. So I have let's just take a snapshot in time. Rather than drawing this thing where it's showing the variation in time as it travels, let's just take a snapshot in time. So I have my E and I have my B, and they're at 90 degrees to each other, and then the propagation is in this direction that's at 90 degrees to that. So let's say that's the X, that's the Y, that's the Z axis, and these guys are at 90 degrees and those guys are at 90 degrees. So it's an orthogonal system. I can define a vector. It's called a pointing vector. It's named after a person, which represents the effect of these 2 guys. And what we say is that EM waves transfer energy through space. The rate of energy transfer is given by the pointing vector, and S is defined as 1 over mu naught E cross B. Point to E, go to B, yeah, it's going to be in that direction. The magnitude of the pointing vector represents the power per unit area. That would be watts per square meter along the direction of the wave propagation. The intensity of the wave is given by, so the intensity of the wave is equal to the magnitude of your pointing vector, which is Emax Bmax over 2 mu naught. That's the take home. And if I remember that Bmax times C is equal to Emax, then I can derive these next 2 equations. So if I say, well, Bmax, let's just substitute, that gets me, what would that be? That would be, if I substitute in for Emax, I would get C times Bmax squared over 2 mu naught. So that's that guy. And if I substitute in the other way, I'd get that guy. So if I substitute in for Bmax, for Emax, I get this. If I take the same equation and now substitute in for B max, I get E max squared over 2 mu c. So I get that guy. So I don't bother with these second two equations. I can figure those equations out. What I remember is that guy. And again, for me, it's one of those things where I learn it as I need it because it's not in my long-term memory. So E max, B max over 2 mu naught. So radiant energy from the sun comes as a plane wave of intensity 600 watts per square meter. So I is equal to 600 watts per square meter. And we say, what is the peak value of its magnetic field component? So we have B max. And again, I'm picturing this thing where it's, I don't want to know what the peak value of the magnetic field is. What's the biggest value? So we said I is equal to S, which equals B max, E max over, what was it, 2 mu naught? And I remember A, B, C, D, E, so B max is equal to C, no, B max, which way around is it? Is it B max equals or B max times is equal to E max? I got to go back and have a look. It's going to be, what was it? It is B max C. So B max C. So B max C is equal to that. So then I say, well, I is equal to S, which equals, now what do I want? I want B max. So I want to get rid of my E max. So I go B max, I'm going to say B max C over 2 mu naught. So I is equal to S, which equals B max, sorry, that's what I want to find out. So 600 is equal to S, which equals B max squared times 3 times 10 to the 8 over 2 mu naught. So B max squared is equal to 600 times 2 mu naught, taking that to the other side, over 3 times 10 to the 8, which equals 400 times 10 to the minus 8 mu naught. So B max is equal to the square root of that. And what would that unit be? Tesla. So we can look at the sun and we can measure its intensity and we can figure out how strong the magnetic field is, you know, as part of that EM radiation. By the way, just, is this a realistic number? 600 watts per square meter, is that from the sun to our planet? Is that, I mean, a 100 watt light bulb is a reading lamp. It's a very strong reading lamp, yeah? On a summer's day, on the surface of the earth, in Florida, noontime, about 1,000 watts per square meter is the solar radiation that we get. It's amazing. I mean, we spend an arm and a leg getting that energy out of our houses. So we buy air conditioning systems to get the energy out of our houses. And then we go and buy electricity to run our television set. I mean, it's kind of laughable when you think about it. But we buy electricity to get energy, to run a machine, to get rid of energy.
It's not
Pardon?
It's not from the sun.
Yeah, it's the craziest thing out. I mean, if you just didn't, if you came from another planet, you'd kind of say, you guys are just, you know, what are you on? It's like, if we go above the Earth's atmosphere, the solar constant, so-called, because it's pretty, you know, it's the sun just radiates, 1200. Now you know, can you get it from there? No, but you know, even in Germany, which is not the sunniest place out, there's enough solar energy that you can harvest an awful lot of solar energy in a cloudy environment. The difference in the insolation is the how much energy, how much incident solar radiation we get between like the north of our country and the bottom of our country. It's a factor of 2 to 1, which if you think about it means that Maine is about half as sunny as Florida, and Florida is pretty sunny, you know. So I'm still always, you know, I go back to England and I see windmills everywhere, and I see solar panels in lots of places, and I'm just frankly stunned that the Sunshine State is not just doing an awful lot more with solar, you know, both on a personal basis but also on a commercial basis. It's just, I find it just amazing. Last little thing. This is our last little thing, and then we're just about done. So, famous experiment. You take basically a plate, 4 plates, and you kind of stick them together. So it's like that. It's like, if looking down from above, it's like a water wheel. And you paint one side black, and the other side is white. And then that side's black, and the other side is white. And then that side black, and the other side is white. And that side is black, and the other side is white. And you shine sunlight on it, and the thing starts to spin. And the idea is this: on the black surface, the photon of light was absorbed, and on the white surface, the photon of light was reflected. Now, when we did Physics 1 and we did about change of momentum, force equals change of momentum, remember what Newton didn't say F equals ma. Newton said F equals dp by dt, which is the same thing, which equals delta p by delta t, oops, which equals p final minus p initial over t final minus t initial. So if I have a change in momentum in a given time, I will get a force, or I get a change in momentum in a given time if I have a force. And if I look at this, my momentum afterwards is 0, and my momentum before is equal to, let's call it p, because it got absorbed, the final momentum 0. If I look down here, the momentum at the end is minus p because it's going to the left, minus the momentum before is p, which equals minus 2p, minus p. So we can see we get a bigger change in momentum when we have reflection than we do when we have absorption. Yeah? The person who made most money out of the gold rush was a guy who invented a water wheel which had little cups on it, as opposed to planks. And what happened was the water came in and had to go back, and it was a really efficient water wheel. Whereas before that, they just had planks, and the water would come and go sideways, and so it wasn't as powerful. And because he was selling that to all the miners, he made more money than any of them did. You know, got a patent on it, and, you know, it's kind of like, did really, really well. The supplier often does better than the people who are taking the risk, kind of thing. Because I know you're going to need a water wheel. I don't know if you're going to find any gold. You know, it's like food services. You got to eat. You know, you might make it rich, but you got to eat. So it's a surefire business in a way. So this idea about being able to make something bounce back is really good for creating a force by a change of momentum. And that's what this does. The reflection makes it bounce back. So you can have twice the force or more force on the white side than you do on the black side. So this thing should spin. And it should spin in such a way that the white side is left behind. So it should spin that way. It should spin with the black side always leading and the white side following. Does that make sense? Because it's the reflection on the white side that causes twice the force. And you go to Mosey and you buy one of these things they're called a radiometer, and it spins. But it spins the wrong way. And when you look at the bottom, because you've bought a set of these and you're outraged that it's not working the right way, and you look at the bottom and it says this system rotates because of solar radiant energy. And it does. It doesn't rotate the right way though, so you go, what's going on? What's going on is inside those radiometers that you buy at the science store. They cost about $5. You put them on your windowsill and it spins all summer long. You know, those things, they work because there's a partial pressure of gas inside. And what happens is the black side absorbs more light than the white side does. And so the black side gets warmer. And so the black side heats up the gas near it. And so the black side has like a little jet engine pushing it. So rather than going with the black side first, the white side goes first. It still spins because of radiant energy. So it turns out one's called, so this one which is to do with heat is called a crux radiometer. And I think the one that's to do with true light is, I think it's a Laue radiometer. But they're really hard to make. And they're like a magnitude. They're much harder to make. So you don't see many of them. So basically what we can say is that the change in momentum P is equal to U over C, the energy over the speed of light. And for reflected light, P equals 2U over C. Momentum transfer creates pressure. Pressure is equal to force per unit area. So 1 of the area times dP by dt, because that's what force is. And then P is equal to F over A, which equals 1 over A dP by dt, which equals 1 over A du over C by dt, which equals 1 over C du by dt over A. And recognizing the pointing vector, that this is a pointing vector equals S. And so P is equal to S over C, or if it's a reflective surface, P is equal to 2S over C. And S was equal to the intensity. By the way, the solar radiation pressure in reality is about 5 times 10 to the minus 6 newtons per square meter. So if I have a square meter of sail, it will have 5 micronewtons on it, or 5 millionths of the weight of an apple on it. Not much, but you know, maybe I can get a big area. It's been used. NASA used the solar radiation pressure to adjust the course of Mariner 10 back in the day when it was hard enough to get the spaceship into space and you wanted it to go a long way. They didn't have fuel to burn. It was like, you know, but they wanted to adjust its trajectory. And so they used the force on the solar cell, to these solar cells, and they tilted one out of the sun and put one into the sun and just used it to tilt the direction of the spaceship. So it's kind of clever. It wasn't designed, I don't believe they designed that in mind. It just fortuitously they could do it. So for absorption, P equals S over C. For reflection, P equals 2S over C. So find the force exerted by reflection of light off a mirror. So I have reflection of light off a mirror. So P is equal to, what was it, 2s over c? That's my basic message. The mirror has a cross-sectional area, A, is equal to 3 times 10 to the 7 square meters. And intensity, I know it's intensity because it's got watts per square meter. So I'm using the units to tell me what it is. Well, it says intensity there actually. But I'm really looking at the units. And that intensity equals the average Poynting vector, and that equals 2.6 times 10 to the 5 watts per meter square. So I go, oh, okay, the pressure is equal to 2 times the Poynting vector, which is 2.6 times 10 to the 5 over 3 times 10 to the 8, which equals 5.2 times 10 to the 5 over 3 times 10 to the 8. So the pressure is equal to 1 carry 2, 7 carry 1 times 10 to the, what's that going to be, minus 3. And what's pressure measured in? Anybody? Pascal. And what is Pascal in terms of newtons and meters?
Newtons per meter squared.
It's a newton per square meter, good. So that's newtons per square meter. And I want to find the force. Oh, look at that, force. So pressure equals force per unit area. So force equals pressure times area. So force is equal to my pressure, 1.7 times 10 to the minus 3 times my area, and my area we just said was 3 times 10 to the 7. So my force is equal to 5.1 times 10 to the 4 newtons. So, then last little bit. When we look at this electromagnetic radiation, we find a huge continuum of possible colors. So light is EM radiation, so are microwaves, so are radio waves, so are gamma rays, so are X-rays. We tend to think of these things as being distinctly different, and they're produced by different means. We don't, you know, we don't have a big light bulb at the radio station, you know. But it don't look like a big light bulb. But in a way it is. It's emitting electromagnetic radiation. It happens to be outside our visible range. So we don't see it. But it's bright, it's there. And it's just a different colour. This tends to come out more in astronomy, because in astronomy you have glowing objects that have a range of colours going from the reddest red to the bluest blue. But then you find there's other stuff out there that you can't even see. You find radio clouds that you can't see, X-ray clouds that you cannot see. There's a whole bunch of stuff out there that can be quite energetic that you cannot see. There's the whole sky is aglow with microwave radiation. Just it's like the afterglow of the Big Bang. We just can't see all those things. Biologically, we made a decision as animals. We decided, what colour shall we develop eyes that are sensitive to? And we chose to make our eyes sensitive to the dominant frequencies created by our star. So we look at basically the colours around the colour of our star. And the choice we made was we won't be very observant at night when the star is over the horizon, but we'll be very observant during the day. Always sleep at night. Other animals made different decisions. Bees, for instance, can see UV light much better than we can. And so when they look at a flower, they don't see a yellow buttercup. They see a yellow buttercup with like landing strips. There's like dots pointing towards where the pollen is. The plant is saying, I'm here, come here, you know. And the bee gets a lot more information than a flower than we get because it can see those colours that we cannot see. And for us, there's like 3 primary colours, and there's a shrimp, and it has something like 21 different receptors for different colours. So it kind of like sees colours in far more, it's like complex colours than we can see. It's just, why? Who knows why? It's serving some useful purpose. So don't get the idea that radio is completely different from light, is completely different from X-rays. They're all the same stuff. It's just our eyes. We decided to look at reflected sunlight rather than the glowing light of objects. But we could have developed eyes which would have been for the glowing light of objects. You can get a little infrared camera and you can follow people on a cold night by the heat left by their footsteps when they leave a warm room. You can see it on the pavement where they... when I was in Japan, I was on our booth selling electron beam equipment, and on the booth over the hallway, there was a guy selling infrared cameras for medical purposes. And when you're demonstrating instruments, you want to get people to see and take notice of your instruments. So there's usually some shtick that you have. That I saw one company that they had a magician would show up and do card tricks. It was like, oh, come on, who cares, you know? But they did it. This guy, his party piece was every like hour or half hour, he would step in front of the camera and hold his hand up, and you see a false colour image of his hand because you can't see infrared, so you're not seeing the colour of his hand, you're seeing the infrared colour of his hand, but you've got to make it visible, so it's called false colour. And it would be blue. And he'd take a cigarette out and he'd light it and take a drag, and his hand would turn red. Because as soon as he took the cigarette, it constricted his blood vessels, which cooled his hand. The temperature changed, and you could see it on the... So he's showing, look how sensitive my camera is. I take a drag from a cigarette, and there's a clear difference in my hand. We chose to just look at reflected sunlight. Okay. So that being said, test time. Let's have a look. So there's 3 big things I look at. There's basically, frankly, there's that calculation. There's that calculation. There's that calculation. So it's going to be one of those 3. So just get familiar. Learn those equations now, and then by the time the test comes, it'll be fine. But nothing sneaky. It's just, here it is. Do you know it?